welcome to this problem walkthrough. Today, we will be solving problem number 1709, titled Biggest Window Between Visits. This challenge focuses on identifying the largest gap between user visits, and will explore multiple approaches to find the most efficient solution. Let's dive in and tackle this problem together. To solve the problem of identifying the biggest window between repeated visits, we explored multiple approaches to find the most efficient solution. The first option is the brute force approach, where we iterate through the dataset and, for each element, search for other occurrences of the same value. Each time we find a match, we calculate the gap between their indices or timestamps and track the maximum gap encountered. However, this method has a time complexity of n squared, as it involves nested iterations, making it highly inefficient for large datasets. Its only advantage is that it requires no additional memory, with a space complexity of 1. The second approach is a hash map with a single pass. Here, as we iterate through the dataset, we use a hash map to store the last occurrence of each element. If an element has been seen before, we calculate the gap between the current index and the last stored index, updating the maximum gap if needed. This method is much more efficient, with a time complexity of n and a space complexity of n, as the hash map stores each unique element. This approach eliminates the inefficiency of nested iterations and is well suited for larger datasets. The hash map approach offers efficiencies that the brute force method lacks, but another alternative is the sorting method combined with the two-pointer technique. In this approach, we first pair each element with its index and then sort the dataset based on the element values. This groups identical elements together, making it easier to locate repeated values. After sorting, we use a two-pointer technique to find the maximum gap between indices of identical elements. While this approach is straightforward to implement and can be useful when sorting is required for other operations, it is not as efficient as the hash map method. The sorting step dominates the time complexity, making it n log n, and it requires additional space for the auxiliary array, resulting in a space complexity of n. Considering these factors, we selected the hash map with a single pass as the chosen strategy. It is optimal in terms of time complexity, requiring only n, and avoids the overhead of sorting and preprocessing. Its simplicity and efficiency make it well suited to handle even the largest datasets. The chosen approach relies on several key observations that simplify the problem. First, the maximum gap can only occur when an element is repeated, meaning we can ignore any pairs of indices where the values differ. This insight significantly narrows the scope of the problem. Second, storing only the last occurrence of an element is sufficient for calculating gaps. Once we find a larger gap, earlier occurrences become irrelevant, allowing us to focus solely on the most recent data. Finally, the hash map provides constant time updates and lookups, making it the ideal data structure for this problem. These factors combined highlight why the hash map approach is superior. While brute force is exponentially slower and sorting introduces unnecessary preprocessing overhead, the hash map solution is both time efficient and memory efficient, ensuring it performs well across all input sizes. It balances practicality with performance, making it the most logical choice. Each of the approaches we considered comes with its own trade-offs. The brute force method is simple and easy to implement but lacks efficiency, making it unsuitable for real-world applications with large datasets. The sorting method with two pointers improves efficiency but introduces additional preprocessing steps, increasing its runtime and memory usage. On the other hand, the hash map approach offers the best combination of speed and scalability. It achieves optimal time complexity of n, and handles edge cases like duplicate values and large datasets effectively. By storing only the essential information, the last occurrence of each value, it minimizes memory usage as well. In conclusion, the hash map approach strikes the perfect balance between speed, simplicity, and scalability, making it the clear choice for solving the biggest window between visits problem efficiently and effectively. In this problem, we aim to find the largest gap, or window, between visits for a series of repeated events. Each event is represented by a number in an array, and the position of that number corresponds to the timestamp or index of the visit. For example, in an array like 5, 3, 5, 1, 3, 4, the event ID 5 appears at indices 0 and 2, so the gap between the two visits is 2. Our task is to determine the largest such interval across all repeated events in the array. the output will be the maximum gap between occurrences of the same event, and if no repeated events exist, the output should be 0. To solve this problem, we start by analyzing the requirements. First, we need to identify all events that are repeated in the input array. For each repeated event, we'll calculate the difference between successive indices where it appears. Finally, we return the maximum gap found across all events. A brute force solution involves using a nested loop. The outer loop scans each element in the array, while the inner loop checks all subsequent elements to find matching events. If a match is found, we calculate the gap between their indices and keep track of the largest gap. However, this approach has a time complexity of n squared, which is inefficient for large datasets. To optimize, we can use a hash map to track the last occurrence of each event, allowing us to calculate gaps in a single pass. The optimized solution involves using a hash map to store the last index where each event was seen, as well as a variable to track the maximum gap found so far. We initialize an empty hash map called last_seen and set max_gap to 0. Then, we iterate through the array with an index I. If the current event already exists in last_seen, we calculate the gap between the current index and its last recorded index. If this gap is larger than max_gap, we update max_gap. Regardless, we update the event's entry in the hash map to the current index. If no repeated events are found during the traversal, max_gap remains 0. This approach ensures a time complexity of n, as we only traverse the array once, and a space complexity of k, where k is the number of unique events in the array. The hash map is central to why this approach is efficient. By using a hash map, we can access the last occurrence of any event in constant time, 1. This eliminates the need for nested loops, reducing the time complexity from n squared to n. There are also some important edge cases to consider. If there are no repeated events in the array, we should return 0, as no gaps exist. Similarly, if all events are unique, the output should also be 0. For large datasets, the hash map ensures efficient memory usage since it only stores entries for unique events. The key insight here is that the problem boils down to efficiently tracking the last occurrence of each event, which makes the hash map an ideal choice. The two main components of our solution are the hash map and the variable max_gap. The hash map, or dictionary, has keys representing event IDs and values representing the last index where each event was seen. This allows us to calculate gaps efficiently as we iterate through the array. The max_gap variable keeps track of the largest gap encountered so far during the traversal. Together, these data structures ensure that our algorithm is both time and space efficient, making it well suited for large datasets. Let's walk through an example to see how the algorithm works in practice. Given the input array 5, 3, 5, 1, 3, 4, we start by initializing last_seen as an empty dictionary and max_gap as 0. At index 0, the event is 5. Since 5 is not in last_seen, we add it with the value 0. At index 1, the event is 3, which is also new, so we add it with the value 1. At index 2, the event is 5, which we've seen before at index 0. The gap between these indices is 2, so we update max_gap to 2 and update last_seen, 5, to 2. At index 3, the event is 1, which is new, so we add it to the hash map. At index 4, we encounter event 3 again. For event 3 at index 4, we find it was last seen at index 1. The gap between these indices is 3, which is greater than the current max_gap of 2. We update max_gap to 3 and update last_seen, 3, to 4. Finally, at index 5, the event is 4, which is new, so we add it to the hash map. At the end of the traversal, the largest gap found is 3, so the output is 3. In terms of complexity, the algorithm runs in n time since we traverse the array once, and it uses k space, where k is the number of unique events. By leveraging a hash map, we achieve an efficient solution that handles edge cases and scales well with large datasets. The given problem is to find the largest gap between any two occurrences of the same element in an array. The solution uses a dictionary to efficiently keep track of the last index where each element was seen. For every element in the array, if it has been seen before, we we calculate the gap between its current index and its last seen index. The maximum gap found during the iteration is updated accordingly. 1. Initialize data structures. We start with an empty dictionary last_seen to store the last index where each element was observed. We also initialize max_gap to -1, as we need to return -1 if no element appears more than once. 2. Iterate through the array. Using a for loop with enumerate, we iterate over the array, keeping track of both the index, I, and the value, value. 3. Check previous occurrence. If the current element value exists in the last_seen dictionary, it means it has been seen before. We calculate the gap as the difference between the current index I and the last recorded index of value in last_seen. For update maximum gap, if the calculated gap is larger than the current max_gap, we update max_gap. 5. Update last seen index. Regardless of whether the element has been seen before, we update its last seen index in the dictionary to the current index I. 6. Return the result. After iterating through the array, we return the max_gap. If no element occurs more than once, the function correctly returns -1. This approach is efficient with a time complexity of O(n), where n is the length of the array, as we perform a single pass through the array and dictionary operations, insert and lookup, are O(1) on average. The space complexity is O(u), where u is the number of unique elements in the array, as we store each unique element in the dictionary. This is the Java implementation of the biggest window between visits problem. The logic mirrors the Python solution, using a hash map to track the last seen index of each value in the array. The main difference lies in Java-specific syntax, such as explicit type declarations and the use of Java's map and math utilities. The method iterates through the array, calculating and updating the maximum gap between repeated values as it encounters them. The final result is returned as an integer. To solve this problem, we start by initializing two variables, last_seen, an empty dictionary to track the last index where each element appeared, and max_gap, which is initially set to -1. Now, as we iterate through the input array 1, 2, 3, 1, 4, 2, we process each value step by step. For the first three indices, values 1, 2, and 3 are new to last_seen, so we simply record their indices without calculating any gaps. When we reach index 3, we encounter the value 1 again, which was last seen at index 0. The gap between these indices is 3 is 0, which equals 3. We then update max_gap to 3, as it's larger than the initial value of -1. We also update last_seen to reflect the new index 4(1). At index 4, the value 4 is new, so we record its index. Finally, at index 5, the value 2 reappears, last seen at index 1. The gap here is 5, 1 equals 4, which becomes the new max_gap, as it is larger than the previous value of 3. By the end of the iteration, our max_gap is 4, and last_seen contains the most recent indices of all elements. At this point, we conclude the first example with a final output of max_gap equals 4. Moving on to the second example, the input array is 5, 6, 7, 8. Again, we initialize last_seen as an empty dictionary and max_gap as -1. As we iterate through the array, each value 5, 6, 7, and 8 is new to last_seen, so we simply record their indices. Since there are no repeated elements in the array, no gaps are calculated, and max_gap remains -1 throughout the process. The dictionary last_seen ends up storing the indices of all 4 unique elements, but because no values reappear, there's no opportunity to update max_gap. With no repeated elements to calculate a gap, the final output for the second example is -1. Now let's examine the third example, where all elements in the input array 9, 9, 9, 9 are identical. We again initialize last_seen as an empty dictionary and max_gap as -1. As we start iterating, the first value 9 is recorded at index 0 in last_seen because it's new. At index 1, we encounter 9 again. Since it was last seen at index 0, we calculate the gap as 1 is 0 equals 1. This updates max_gap to 1, as it is larger than the initial value of -1. We also update last_seen to reflect the new index of 9. At index 2, we see 9 once more, last seen at index 1. The gap is 2, 1 equals 1, which matches the current max_gap, so no update is needed. Similarly, at index 3, the gap is calculated as 3, 2 equals 1, and again, max_gap remains unchanged. After processing all elements, we update last_scene to store the most recent index of 9, which is now 3. The final max_gap remains 1, as that was the largest gap found between consecutive occurrences of 9. Therefore, the output for this example is 1. These examples demonstrate how the algorithm handles a variety of input cases, from arrays with repeated elements to those with all unique elements, and finally, arrays where all elements are the same. The time complexity of this algorithm is O(n), where n represents the length of the input array. This efficiency is achieved through the use of a single for loop, which iterates over the array exactly n times. This means the dominant factor in our time complexity is the number of elements in the array. Within the loop, dictionary operations play a crucial role. Checking if a value exists in the dictionary, updating it, or inserting new entries are all performed in constant time, O(1), thanks to Python's hash table implementation. Arithmetic operations, like calculating the gap between indices, are also O(1). When we combine these steps, the total time complexity is O(n), iterations multiplied by O(1), operations per iteration, which simplifies to O(n). This makes the algorithm highly efficient for large input arrays. Now, let's consider the different scenarios for time complexity. In the best case, even if there are no repeated elements in the array, the loop still traverses the entire array, resulting in O(n). The average case is also O(n), as the algorithm performs the same constant time dictionary operations for every element, regardless of the input distribution. In the worst case, where all elements in the array are identical, the loop still processes each element exactly once, maintaining an O(n) complexity. Turning to the space complexity, it depends on the number of unique elements in the array, denoted as U. While the input array itself requires O(n) space, this is part of the input and not additional memory usage. The dictionary, however, stores one entry for each unique element, and in the worst case, where all elements are unique, it will contain U equals n entries. Each key value pair in the dictionary takes constant space, so the total space used by the dictionary is O(u). Additionally, the auxiliary variables used in this algorithm, such as max_gap and the loop index I, require only O(1) space. This means that aside from the dictionary, no other significant memory is allocated, and the overall auxiliary space usage remains O(u), where U is the number of unique elements. Comparing this with the brute force approach highlights the optimization. A naive solution would involve two nested loops, where the outer loop iterates through all elements of the array, and the inner loop compares every subsequent pair of indices. This approach results in a time complexity of O(n²) in the worst case, as it performs redundant comparisons. In contrast, the optimized approach uses a dictionary to track the last occurrence of each element, eliminating the need for nested loops. This drastically reduces the time complexity to O(n), making it far more efficient. Finally, let's solidify our understanding with a mathematical proof of the optimized approach. The loop runs exactly n times, and each iteration involves constant time operations such as dictionary lookups and updates. Multiplying these, the total time complexity is O(n*(O1), which equals O(n). For space complexity, the dictionary stores at most U entries, where U is the number of unique elements and is always less than or equal to n. This means the space complexity is O(u), determined by the number of unique values rather than the total number of elements. To summarize, this algorithm achieves O(n) time complexity and O(u) space complexity, a significant improvement over the O(n² time complexity of the brute force approach. This makes the optimized solution not only efficient for large arrays but also robust across all cases, including best, average, and worst scenarios. When tackling this problem, there are a few common pitfalls to watch out for. First, not sorting the input data is a frequent mistake. If the timestamps or indices are not sorted, you won't be able to calculate the gaps linearly, leading to either incorrect results or inefficiencies. The solution here is simple: always ensure the input is sorted before calculating gaps unless it's explicitly stated that the data is already sorted. Another issue arises when indices are confused with values. For instance, if the input contains indices derived from some other data structure, mixing these up with actual values can lead to logical errors. To avoid this, make sure you clearly track whether you're working with indices or values. Additionally, don't overlook edge cases. Scenarios like having only one visit, duplicate timestamps, or very large gaps can cause runtime errors or unexpected outputs if not handled properly. Testing diverse inputs, including those at the minimum and maximum constraints, is key. Finally, brute force approaches with O, n squared, complexity should be avoided when an O, n log n, solution suffices. For large datasets, sorting followed by a single linear pass is far more efficient and practical. Another point to consider is how you handle duplicates. If timestamps or visits are repeated in the input, failing to address this properly can result in incorrect gap calculations. Be sure to clarify whether duplicates should be ignored or included in your solution. From an interview perspective, this problem is closely related to other maximum gap problems, so recognizing patterns like sorting or bucket-based approaches can be a big advantage. Once the data is sorted, you only need a linear pass to find the largest gap, so avoid unnecessary recalculations. It's also important to ask clarifying questions during interviews, such as whether the timestamps are guaranteed to be pre-sorted, if duplicates are allowed, or what the expected input size is. These questions can help you tailor your approach. Interviewers may also introduce follow-up challenges like memory constraints, which could require a bucket sort or radix sort, or even ask you to adapt the solution for multi-threaded environments. Being prepared for these variations will showcase your problem-solving flexibility. This problem is conceptually linked to several related problems, which makes it a great opportunity to build transferable skills. For example, LeetCode 164, maximum gap, involves finding the largest difference between consecutive elements after sorting, which is directly aligned with the logic here. Similarly, LeetCode 128, longest consecutive sequence, focuses on consecutive subsequences and shares the need for efficient data handling. LeetCode 56, merge intervals, is another relevant example, as it deals with identifying and managing gaps between intervals after sorting. Finally, LeetCode 1465, maximum area of a piece of cake after horizontal and vertical cuts, applies the maximum gap principle to a geometric problem involving cuts. Now, when it comes to alternative approaches, the brute force method is the simplest and involves checking all possible pairs of visits to compute their gaps. While easy to implement, this method is highly inefficient with a time complexity of O, n squared, making it unsuitable for larger inputs. A more practical approach is sorting the timestamps or indices, which has a time complexity of O, n log n, followed by a single linear pass to calculate gaps. This strikes a good balance between simplicity and efficiency, though the sorting step does add some overhead. For even more optimized solutions under certain constraints, you can consider a bucket-based approach. By using bucket sort or radix sort, you can achieve linear time complexity, assuming the input consists of bounded integers. This approach is particularly useful for constrained inputs, but it does require extra memory and careful bucket management to ensure correctness. Another alternative is the sliding window technique, which is well suited for variations involving streaming data. With this method, you can dynamically compute gaps as you iterate through the input. However, this approach may not be applicable to all variations of the problem, as it depends on specific requirements. Ultimately, the method you choose will depend on the problem constraints and the trade-offs between time complexity, memory usage, and implementation complexity. Great job! In this session, we explored how to solve the biggest window between visits problem by analyzing gaps in data. We covered various approaches, their complexities, and practical use cases. Thank you for joining, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!